Good morning. It was a little late for me to put these up, but what we did is we graphed both of these sequences in class, and what we find is this is the sequence minus 1 to the n times 1 minus 1 over n that you're looking at, and you can see to pick out a subsequence that converges is fairly easy. For example, if this is a bounded sequence, here's the subsequence right here. This is my first element, this is my second element, this is my third element, and so forth. If I ignore these elements down here and I look at these elements up here, they're going to be the convergent subsequence. So I can actually see this subsequence. So what Bolzano-Weirstrauss says, which is one of my top 10 favorite theorems, I wonder if I actually do have 10, might have more than 10, but it's in my top 10 for sure. If I have a bounded sequence of real numbers, then Bolzano-Weierstrass says that I have a convergent subsequence. That theorem is called Bolzano-Weierstrass. So let's work some more examples involving that theorem, and that's the one that I gave you in class was xn equals sine n, which threw most of you for a loop, because when you plot this in Excel, you cannot see the subsequence that converges. You think you can initially, but you can't, because what you really see is a mess of points. It's not, the fact is that you're putting in inputs. This is not 1 minus 1 over n, this is sine n. You're putting in inputs of n into sine n that are integers. They're not multiples of pi. So although you might see, you can see that it doesn't appear to be a pattern here. So it's very difficult for me to eyeball this and say that there's a convergent subsequence from it, or what that convergent subsequence is. So these kind of theorems like Bolzano-Weierstrass are not for things that you can easily see. They're the proof that guarantees you that you have a convergent subsequence in something you can't see, like sine n. This is actually bothering me, so I'm going to put up a little thing here. Let's put up a little thing here that says sine n. And give that a shape fill. There we go. Much better. We'll just do a copy, paste, so that we have this out here. All right, so this is sine n that we're looking at. So unlike the previous picture, I could pick out and tell you, here's my convergent subsequence right here. I can actually visualize it. This one I can't. But Bolzano-Weierstrass says that it must have one. So my suspicion looking at this is that probably there's a subsequence in here somewhere that's converging to the soup of this sequence, which looks like it could be 1. I can't even tell you that for sure, but it looks like it might be true. So that was the tricky one about sine n. You will not be able to see that subsequence. The only way to actually verify that particular sequence has a convergent subsequence is through the process of what we call rigorous proof, going back to definitions and first principles. So here's this proof, very elegant. It's a work of art here. I'm going to let S equal the soup of that sequence, xn, an arbitrary sequence. All I know about that sequence is it's bounded. So therefore, because it's a bounded sequence, I know the soup exists. That allows me to tag it with an S. Just like Facebook tagging, I'm going to tag S as the soup of that sequence. I claim that I can find a subsequence that converges to my soup. To see this, I'm going to use the epsilon definition of the soup. The epsilon definition says that, number 1, S is an upper bound of that xn, and for each epsilon greater than 0, that's a real number, there exists an x in the sequence such that S minus epsilon is less than x. Or another way to say that is x belongs to this interval. It's capped by S on the top, and on the bottom it's capped by S minus epsilon. And this could be a closed interval, actually not an open. So the epsilon definition says that this is true for every epsilon. So I can set up, I'm allowed to pick now epsilon because that statement is true for every epsilon. So I'm going to take, for k equals 1, I'm going to set my epsilon equal to 1 over k, which is 1. then by definition of soup, I know there exists an x in this interval where x belongs to the sequence. If x belongs to the sequence, then it's a sequence member. I'm going to label that sequence member with the subscript n sub 1, indicating that it's an element of this sequence. I'm going to do the same thing for k equals 2. I'm going to set epsilon equal to 1 over k, which is 1/2. And then I know by the soup definition that there's an x n2 that belongs to this interval. On and on, I can find x and k's as the element that's in this sequence. So my claim is that these x and k's that I've picked one by one are going to be inside that, are going to convert to the soup. I'm going to illustrate this for you with an example after I finish the proof so you can actually visualize it and see it. So the way we prove convergence, it's like a template. We first start out with epsilon greater than 0 be given. Then I need to find an n. That's my job. So I claim that there exists an n large enough so that I can jack up the value of k so that 1 over k is epsilon. Here's how it works. Suppose you pick epsilon equals 0.10. Can you find a k value that's high enough so that 1 over k is bigger than 0.10? Sure. Take it, k equals 11. So for all the k's bigger than 11, then I'm going to have 1 over k is going to be smaller than 0.1. And so this statement is true that you give me an epsilon, the smaller you give it to me, the bigger I'm going to jack up k. That might seem obvious. I want to give you a word of caution that some profs want that also to be shown. So it's in the world of writing proofs, nothing's actually obvious. You might have to prove every little detail. You'll find out. You'll get a red mark saying you should have shown it. So x and k belongs to that interval. So that means if I expand that interval, I get this. X and k's are bigger than the s's, are smaller than the s's, sorry. So that's positive. So I can slap on the absolute value. These two things are the same thing. And because by just adding the 1 over k to both sides, I get, and subtracting the x and k to this side, I get that this guy over here is less than 1 over k. I'm just messing with this side of the inequality. But 1 over k was set to be less than epsilon. That's the definition of convergence. I have to show, given epsilon greater than 0, there exists a capital N. I've shown you what that capital N is so that this inequality holds. Done. So I had you guys actually do this with sign n, actually find what that subsequence is for epsilon equals 1 over k in my construction of this proof. So for example, if k was 1, then if I think the soup is 1, then what would happen is I'd have to take the soup, which is 1, and drop it by 1. S minus 1 is right here. Can I find a member of that sequence that's above that line? The answer is yes. I'm starting. I could have picked any one of them that's above the line. I'm just going to pick that one. So that's my xn1. It just happened to be the third element in the sequence. See? 1, 2, 3. It's the third element in the sequence, and I can actually see it. That's my xn1. Now I'm going to set k equal to 2. That means I'm going to drop the red bar 1 minus 1/2, which is right here at 1/2. And the question is, can I find an element of the sequence that's above that red bar? And the answer is yes, right here. There's my second element. And there it is. It's sequence member number 7. And so forth. I had you guys in class keep jacking up that red line higher and higher, and each time you're finding a new subsequence member. So that's how we constructed this sequence, that this line is going up in terms of 1 minus 1 over k each time, and I can always find a sequence member above that red line, thereby creating my subsequence, which is going to close down and converge to S. And that's pretty cool. All right, hope you enjoyed that as much as me, and rewatch this several times, just like one of your favorite movies.